Hello, this is Dr. Christy Patton-Lokes, a chemical engineering professor at Missouri S&T. In this series of lessons, we'll be looking at numerical computation techniques or ways of finding roots of equations. In particular, we're going to be looking at a cubic polynomial equation, which was generated for the Pang-Robinson equation of state for chlorine. And we're going to be specifically looking at three different cases, one where we have the temperature is 500 Kelvin and the pressure is 150 bar, another at 200 Kelvin and 1 bar, and another at 415 Kelvin and 75 bar. And we're going to start by looking at this using graphical techniques. So let me close this up, and I have here an Excel file where I've already put in the data for chlorine in this paler yellow up here, and I then have the given state. So we're starting with this first state of 520 Kelvin and 150 bar. And we're basing it on the Pang-Robinson equation of state, and these equations here first reevaluate the temperature as reduced temperature and reduced pressure, and then calculate the parameters for the Pang-Robinson equation, and the equations are shown in those there if you wanted to look at them. This really isn't about the thermodynamic background. We're really focusing this time on just getting solutions. Now, if you use this equation of state with these values of kappa, alpha, or A and B, then we end up with this third order polynomial as the appropriate expression for Z, the compressibility factor. And if we're wanting to do this graphically, then what I want to do is put in values for Z, and I want to put in values for a function of Z. And you want to be able to say that this function of Z is going to be equal to something simple, like 0 would be simple. And so my f of Z is going to be Z cubed plus negative 0.87862 Z squared plus 0.21888 Z minus 0.04488. Okay, and I'm going to be looking for where that is equal to 0. Now Z, the compressibility factor, I expect it to be positive, and I expect it to be no more than slightly greater than 1. So let me just put in some Z's here, and I'm going to increment this fairly small. And we'll extend this down to, maybe 1.1. I mean, Z can be greater than 1, but usually it isn't much greater than 1. Okay, so 1.1. There we go. So I have values of Z, and I'm now going to put in my function. And the function is going to be Z cubed plus this number in front of the Z squared plus this number in front of the Z plus this last number here. And I'm going to want to duplicate that down, so I'm going to come in here and I'm going to edit that, and I'm going to use the F4 key to change the D, F, and H 14 entries. So I'm just going to hit F4. It's going to insert dollar signs, which means it will be using absolute references instead of relative references, but I want to use relative references on the Z. So if I do that, now then I can copy this and as I scroll through here, I see sometimes it's positive, sometimes it's negative. So to go from negative to positive, it must have crossed 0 someplace. So I do have my answer trapped. And let's look at this. So we're going to insert a graph. And if I look at this here, I'm looking for, this is my f of Z on this axis and Z is across here. And I see that the answer is going to be somewhere around this 0.644 value. Okay. Now, a graph like this, I will say it's very bad form to not label your axes. So therefore, let's at least, well, I'll just add chart elements. So my axis across the bottom is Z, And I want to add this. This is my f of z. Now remember, f of z was just what I made up, and I'm looking for where it's equal to 0. And so I can look at this, and I could, you know, if I was okay with this, I could either do a better graph, hone in on just that one spot there, or I could look at this and say, it's really close to 0.65. Put your mouse over there. Yeah, 0.65 is really close if I go a little smaller. And I can do that, and I can get a pretty good estimate. But I do see that the answer is going to be over here in the between 0.6 and 0.7 region. So graphically, I can get some answers, and they're not that hard to do. Let's look at these other two cases that I had mentioned. So my next case was 200 Kelvin and 1 bar. And you'll see that it recalculated all my parameters. My polynomial has now changed. And if we look at this, we see that, oh, the answer is very close to 0. Okay? And if we look at this over here, yes, that's indeed what we're seeing. Okay? Something very close to 0 is going to be my answer. This is going to be something where it's more liquid-like, the other is where it's more vapor-like. Okay. Notice I do have another value of the root over here, so I definitely have 2 roots. Okay. Solving this is going to be a little different, but graphically it's like, okay, well, I've definitely got an answer there. Now it looks like I have 2 answers right in this region. Okay. And I could, again, use this, and I've gotten some information from the graph, and it certainly gives me a good first estimate of what the answer would be for later solutions. But sometimes it's a little more unclear, and so I picked the case where the temperature is 415 and the pressure is 75 bar. And when I did that one, what I discovered is that I have this long, flat region of ugliness that I really couldn't visually tell you. You know, I could zoom in a little bit better. I could go through and look at my values and see that, okay, it pops between positive and negative somewhere in there. But really, graphically, some graphs are harder to use than others. So what we want is some more robust techniques that will actually get at the answer. Graphical is, I think, an excellent way to start, but it's not very good for getting a refined answer. And it's not very good if you have to do a lot of different problems over and over and over again. This wasn't so bad because I've set it up so that it will automatically graph. And I could even change, by changing up here, I could change my compound from chlorine to something else pretty easily. Okay? And I would get a graph that would get me approximate answers. But can I do better? So we're going to look at approximately 6 techniques that are going to be improvements over the simple graphical method. All right? Thank you very much for your time.